So our next speaker is José Luis Teruel from Universidade de Brasília. He's going to talk about complete surfaces with non-positive curvature in space forms.
Thank you very much. Good morning to everybody. In the first place, I want to thank the organizing committee. I want to thank the organizing committee for inviting me here to stay here and to talk about some results about complete surfaces with non-positive curvature in space forms. All these results are a joint work with José Antonio Galvez and Antonio Martinez from the University of Granada. First of all, I'm going to introduce the motivation of the problem we're going to study here this lecture. At the very beginning, Beltrami, by using results of Minding, he proves that any surface in R3 with constant negative curvature has locally the same geometry as the hyperbolic plane. And he realized for the first time the difficulties of treating this kind of surfaces globally in R3. For the first time, Hilbert resolved that problem successfully. He proved that the hyperbolic 2 space cannot be immersed into R3. And a little more, because you know that constant negative curved surfaces in R3 are isometric to a portion of the hyperbolic plane. And then it's not possible to extend this kind of surfaces into until infinity without the appearance of singularities. It cannot do with smoothly. Okay. To understand better the results I'm going to present in this introduction, I'm going to use this concept of curvature diagram in order to explain better these results and to compare them. Okay. This curvature diagram is nothing but a representation, a two-dimensional representation of the curvature and the mean curvature of the surface. No? You can represent here, in each point, the respective values of the Gaussian curvature and the mean curvature of the points of the surface. Okay, this area here is an area of non-existent surfaces because, it's an area of non-existent. Surfaces can be represented here. The Hilbert Theorem says that any complete surface with constant negative curvature can be represented in this straight line parallel to the h-axis. This is a non-existence area for the Hilbert Theorem. Okay? This result drew the attention of another mathematicians, in special Kohn Vossen. He writes a conjecture about this theorem, related with this theorem. He wondered, negative constant curvature surfaces cannot be immersed in R3. What if that curvature was non-constant, not a constant function? Maybe a function bounded from above by a negative constant. And then he wondered about that possibility, and he opened a work line related with Hilbert's theorem. mathematicians began to work in that topic, and in 1955, Heinz gave a partial solution of that problem. He proved that there not exist graphs, complete graphs in R3 isometrically embedded when their function curvature is bounded from above for a negative constant. He solved partially that problem, but not totally. A few years later, in 1964, Efimov gave a successful answer to that Hilbert-Cohn-Bose conjecture. He gave a positive answer. He proved that indeed there now exist those kind of surfaces isometrically immersed in R3. In this curvature diagram, we can compare such results, and we can observe that the non-existence area for the Efimov theorem indeed extends the non-existence area for Hilbert's theorem. Then we can observe that clearly Efimov's theorem extends Hilbert's theorem. Efimov himself, he tried to extend again his own theorem, and he reached a pair of results, one in 1968 and another one in 1975. In 1968, he proved that his own theorem still remains true, weakening the hypothesis on the curvature function of the surface. And in 1975, he proved that the half hyperbolic plane cannot be immersed in R3 with C4 smooth. It's interesting because he opened two new work lines in order to extend this theorem, this result, with problems related with Hilbert's theorem. He opened a first work line awakening the hypothesis, the conditions on the curvature, and another allowing a certain type of border in the surface. This is quite an interesting thing. Later on, I'm going to explain a little bit more. The result of 1975 of Efimov was improved 1 year later by Vorobeva. She proved that the same theorem, so the same thing, the half hyperbolic plane, cannot be immersed with C2 smooth. Another problems related with Hilbert's theorem are of interest for us. For example, this conjecture raised by John Milnor in 1966. And this conjecture states that you suppose a surface complete without umbilic points and immersed in R3, such that the sum of the squares of the principal curvatures of the surface is bounded far away from zero. In that terms, can occur two things. The first one is the surface is flat. Other, the curvature of the surface necessarily change its sign. We can compare the respective non-existence area, and if the conjecture of Milnor's conjecture was true for negative curvature of the surface, okay, non-positive curvature of the surface, then we can observe that this theorem, I say if it was true, allow the existence in the surface of a sequence of points such that their respective principal curvatures tend simultaneously to 0. It doesn't occur in the Efimov theorem. Efimov can guarantee sequences of points such that its extrinsic curvature tends to 0. The product of the principal curvatures tends to 0. We can observe here that indeed Milnor's theorem, if it was true for non-positive curvature, extends Efimov's theorem. Okay, that result, that conjecture, unfortunately, is not solved today. Still not solved. It remains unsolved today. But Smith and Xavier, in 1987, they solved partially this conjecture of Milnor. They prove, in fact, that any complete surface immersed in R3 with no positive curvature, if one of their principal curvatures is bounded far away from 0, separated from 0, then the surface must be a generalized cylinder. And even that result is not a total solution of the problem, we can answer, we can wonder if that result extends Efimov somehow. We can check out here, observing the respective non-existence areas of Smith-Xavier and Efimov. Unfortunately, those existence areas are not related with an inclusion relation. So are two different theorems related with Hilbert Theorem, but they are not related. Smith-Xavier does not extend Efimov. Okay. Recently, in 2001, Schlenker, he tried to obtain more results similar to Efimov's theorem, but in another space forms, in non-Euclidean space forms. Okay? We know that those non-Euclidean space forms are the hyperbolic space and the sphere, three-dimensional sphere. Okay, he proved that any complete surface with their natural conditions on the curvature K cannot be immersed in H3 and S3, but with an additional hypothesis, with an additional condition of the modulus of the gradient vector of the curvature. It is not exactly an equivalent of Efimov's theorem. We can say that the result is an Efimov type theorem. But anyway, he opened a new work line again of obtaining results related with the Efimov theorem or Hilbert theorem. This work line is to obtain an equivalent theorem, to Efimov's theorem in three-dimensional spaces, non-Euclidean three-dimensional spaces. It's quite interesting. Okay, more recently, the Kodachi pairs theory, they appear as a very useful tool in order to attack classical theorems of the theory of surfaces but in spaces form in space forms different non-Euclidean space forms. See? Why? Because for any immersion of a surface in those spaces, those space forms, the first and the second fundamental form, they form a Kodachi pair. I will explain what a Kodachi pair later. And that means that whatever the space the Kodachi equations hold, those theorems can be translated to another space forms, to another non-Euclidean space forms. That's why Kodachi pair theory is an interesting tool. Okay, this problem, this is not an Efimov type, but it's an equivalent of Efimov theorem. Is what I mean. This true remains as an open problem. Okay. Then, after this introduction, I want to present some results related with the different work lines I presented before. I will summarize those work lines in two. The first work line is related to obtaining an equivalent of Efimov theorem in non-Euclidean three spaces. And the second work line I want to expose here is the extension of Efimov theorem to complete surface of R3, allowing a compact border in the surface. Okay? This is our objective today. To introduce some advances concerning the different work lines related to Efimov theorem before. Summarized in two. Okay? About the first work line, before presenting results concerning space forms, I want to present, to introduce in the first place, a little result concerning space product spaces. Okay? In this work line, one can prove that in a product space of type M2 times R, where M2 is a Riemannian surface with a pole, in these conditions, there are no entire graphs, complete graphs, immersed in those kind of spaces if the curvature of the base of M2 is non-negative and the curvature, the graph, has curvature bounded from above for a negative constant. This result is saying the following. Efimov theorem holds under this equation, under this assumption, this condition, for product spaces. And one can wonder what happens when the curvature of the base is not is negative. Well, in that case, one can construct examples of surfaces satisfying the Efimov conditions and isometrically immersed in those space products, satisfying M2 is a negative curve Riemannian surface. In fact, it's possible to construct some examples of rotation surfaces. They are not graphs, but they are surfaces. Rotation surfaces in some special product spaces with negative curve in the base, negative curvature in the base. Okay. Now I'm going to present, to introduce some results concerning space forms. let sigma be an oriented differentiable smooth surface. I'm going to explain some concepts we have to know to understand these results. Okay. A fundamental pair on the surface, sigma is an abstract surface. A fundamental pair on sigma is a pair of real quadratic forms. We denote it for 1 and 2, such that the first one is a Riemannian metric. Okay, the shape operator, we are denoting for A, is defined as the usual form, and the mean curvature, the extrinsic curvature, the principal curvatures of the fundamental pair are defined as usual. Okay, as the half sum of the principal curvatures. Okay. We are saying that principal curvatures of the pair are strictly separated if there exist two constants satisfying this inequality. Okay? Well, a fundamental pair, 1 and 2, is said to be a Kodachi pair if that fundamental pair satisfies the classical Kodachi equation of the theory of surfaces of R3. Well, that for immersions in H3 and S3, 1 and 2 form a Kodachi pair, and because that equation holds in those spaces. Okay? Well, the first result states the following. Let B, let 1 and 2 a Kodachi pair with strictly separated principal curvatures if the surface is complete with non-positive Gaussian curvature, then just can occur one of these two items. Okay? In the first place, one is flat, and the surface is homeomorphic either to a plane, or a cylinder, or a flat torus. Well, the first is not flat. The first fundamental, one, I'm going to call this 1, is not flat, and has, the surface is homeomorphic to a plane, and has total curvature bounded. Okay? Sketch of the proof, this result is as follows. Take a parallel, sigma being A different of 0, such that A times K1 different of 1, A times K2 different of 1. Then, in that this surface is a parallel surface of distance to distance A, and in the direction of the normal. Okay? Then let lambda A, the induced metric, one can prove that we can express this metric in terms of first, second, third. The third is defined as usual, using the shape operator. Okay? And a simple computation gives this relation. Okay? And then we can observe that those parallel has non-negative curvature, and this curvature vanishes if only if vanishes this curvature. And then this curvature, if this curvature was flat, vanishes. If this curvature vanishes, then the curvature for the first vanishes too. And in that case, by Cartan's theorem, the surface is homeomorphic to a quotient like this, where gamma is a discrete group of isometries of R2. That yields plane, cylinder, or the other the flat torus. Sorry?
What is the parallel surface?
The parallel surface, we can obtain it so, no? Translating in the direction of the normal.
What's the parallel space? What's the ambient space?
Yeah, okay. Okay, maybe, okay. I am talking for the next theorem, sorry. This proof can be done in abstract. We can define this metric for this surface and making computations. Okay? Okay. The second item states that by Hilbert's theorem, the total curvature is finite, bounded. Okay. Well, the next result, the following result, is just applying the conditions of the first one out of a compact subset of the surface. Yeah. Then, in those conditions, the later theorem holds too. And by Hilbert, we have the surface is a parabolic type and has finite topology. Okay. These two theorems yield some interesting results of Efimov or Efimov type or Milnor type for immersions in H3 and S3. Okay. In the first place, if we take an immersion with Gauss curvature, okay, with the natural assumption for the curvature, implying the Gauss equation of this ambient, this space form, such that one of the principal curvatures are far away from zero, uniformly far away from zero, then the immersion is not complete. We can obtain this result applying the theorem, the first of the two theorems. And we can obtain a parallel result for S3 under its respective hypothesis for the curvature. Okay. Applying the second one, we can obtain some interesting results too. For example, this one for immersions in the hyperbolic free space. If we impose the conditions out of a compact subset of the surface, then the surface has finite area, it's parabolic, and has finite topology, directly applying the second theorem. and its respective result for the sphere. Just adjusting, just using the Gauss equation here. Okay. Despite the second word line, I'm going to present one result of extension of the Efimov theorem for images in R3. As I said before, we are going to allow some compact border on the surface. Well, to extend the Efimov theorem, we have to understand this result. It's a fundamental result that Efimov used in his paper in order to prove their theorem, his own theorem. It's very important result. We are going to use it. Okay? In order to understand this lemma, I'm going to introduce some concepts we need to understand. First place, consider an immersion R3 with negative curvature and its respective Gauss map. Define the fundamental third form as usual, as the pullback of the metric induced by the space on the sphere. It is just the 3 is the induced metric for the sphere on the surface. Well, if K negative, then 3 is not complete. If we supposing that the surface endowed with this metric is complete, due to the curvature in the sphere is constantly 1, and considering that the surface is connected, then it implies that this metric space must be compact. And it is a contradiction with the assumption, with the conditions on the curvature. This was an observation of Tila Klort in his paper talking about the Efimov theorem. Okay, for that reason, makes sense to talk about the completion, the metric completion of this space 3, this space sigma, endowed with the metric induced by the Gauss map on the surface. Okay, we are going to denote sigma tilde, this completion, and n tilde is going to be the continuous extension of the Gauss map, those points. Let's define the boundary of the completion in that way. Okay. We take starting with a non-geodesic arc, gamma, and a point within this arc. We can construct this rectangle called the stereo rectangle at the point P. In this way, we can construct this rectangle just considering the union of geodesic segments throwing out from the curve gamma in the direction of concavity and of length epsilon. Okay. And the result is a figure like this. A point of concavity P is a point which lies in the completion of a certain of a certain domain U, which in his spherical image in the sphere, this domain contains within a stereo rectangle like this on the at that point, at the point NP, okay, at the point image of P by the Gauss map. Okay, when the computation of the surface the computation for the third fundamental form metric. If that computation don't have concave points, we say the surface endowed with the metric of the third fundamental form is pseudo-convex. Okay? The Efimov lemma says that every the Efimov lemma states that any immersion of a complete surface in the condition of Efimov must satisfy a certain convex property. Okay, this is the convex property that it satisfies. Okay. We are going to say that the reciprocal value of the curvature K has variation with linear estimate if this inequality holds. Okay? This is the hypothesis Efimov used to extend his own theorem in 1968. He weakened the assumption by using this new assumption. We are calling this assumption as the Efimov's weak condition. Okay. From now on, this assumption is going to be the Efimov's weak assumption condition. Observe one thing. In the conditions of the classical Efimov theorem of the 1964, those conditions say that the surface has curvature bounded from above by a negative constant. Okay. If one of these immersions satisfies this condition, it satisfies this condition too, just by taking epsilon 1 equals 0. Then this condition is stronger than this one. Now, from now on, we are calling this condition the Efimov strong condition. Okay? Well, the Efimov lemma says the following. Any C2 immersed surface, complete surface in R3 with negative curvature in the wake conditions of Efimov is a spherical image endowed with the metric of the Gauss map is pseudo-convex. We can observe here the pseudosphere is so. Okay, like this, this proof is based in the construction of a special C1 immersion of one special region G in R2. That construction is local, so we could adapt this result to the new hypothesis, allowing some compact border of the surface. And now we can say that the Efimov's lemma still holds when we allow some compact boundary on the surface. Okay. Well, we're going to present quickly two technical results. Don't have time. Okay. This primary result says that using the Efimov technique, we can join 2 points out of a compact set containing the compact boundary within, adjusting these distances and having a nice area to work and to use this Efimov technique we can prove that any 2 points of the surface out of the compact of a compact subset can be joined by a minimizing geodesic arc from P to K. Okay, this is a sketch of the proof. I don't have time to explain it. The second lemma states that minimizing arc have length at most P. Okay? Well, this is the sketch of the proof. Well, the main results of this work line. We have a surface with compact boundary, situ immersed, complete, with negative curvature, in the weak conditions of Efimov. Then the total curvature is bounded, and in particular is parabolic and has finite topology. 5 more minutes? Okay. Thank you. By using lemmas 2 and 1, we can parameterize the whole region or the whole area of the surface out of a compact subset containing within the compact border of the surface. Okay? In terms, by means of the exponential map of the metric 3. This area is bounded because this area depends on the geodesic curvature of this curve. That curve is the border of the compact set C, containing within the compact boundary of the surface. Okay? And that area is equal to the total curvature in that region, and so it's bounded. By Hilbert Theorem, we get parabolicity and finite topology. Okay. Just by taking a surface, a complete surface without boundary, but imposing conditions out from a compact subset, we can, making a parallel reasoning, we can prove this theorem that states the same, has the same conclusion for immersions without boundary, but imposing those conditions out of a compact space. A compact subset. Okay, here in the figure we can observe that in the compact area there is no control of the conditions about for the curvature, and then the surface can have genus. Okay, and changing the weak condition of Efimov for the strong condition of Efimov in the theorem 2, the same condition of the theorem 2 mass, but changing that condition weak for the strong one, we can get some extra information about the surface. Okay? The surface has finite topology, has finite area, is properly immersed, and NEN is asymptotic to a half-line of R3. I have here the sketch of the proof, but I think I had to end here. Thank you very much.